Welcome you all. Sorry for the delay. There is an unexpected thing happen. So welcome to the last session. I am Ali Çırpan from the Department of Chemistry. I am chairing this session. First speaker from the Department of Chemistry, METÜ, Assistant Professor Dr. Demet Asil Altekin. Demet Hocam graduated from the Department of Chemistry, and she got also her MS degree from the same department. Then she got her PhD degree from the University of Cambridge. Then later on she joined our department. Today she is going to talk about the design of surface passivation technique for the lead telluride quantum dots and application to photovoltaic devices. Demet Hocam.
Ali Hocam, sunumumu online göndermiştim ama Ali Hocam başlayacak mı otomatik?
Evet başlar.
Tamam.
Emre başlatır.
Welcome to you all. I will be talking about the design of surface passivation techniques for telluride quantum dots and their application to photovoltaic devices. Maybe the first question to ask is why quantum dots? Why will we be talking about quantum dots today? We know that all the single junction photovoltaic cells have a limit on their efficiency, which corresponds to 33% of the solar spectrum. And the first energy loss mechanism is due to not absorb photons. We know that when the energy of the photon is less than their band gap, basically no electron hole pairs are created, and it corresponds to a loss of 19% in the solar spectrum. Another major loss mechanism is the thermalization losses, which is around 33%, a significant loss mechanism, and this is due to absorption of photons greater their band gap. We know that the absorption of photons above the band gap creates an electron hole pair, but this time when that electron relaxes back to the first excited state, it releases some heat, and that leads to heating of the cell, which also creates some other loss mechanisms. So this is a very significant loss mechanism, which corresponds to 33%. Another loss mechanism is the extraction losses. We know that not all the extons generated can be collected by the respective electrodes, and this leads to 15% loss in the solar cell technology. And quantum dots offer some unique solutions to those loss mechanisms. First, their band gap can be tuned very easily, and the materials that have very large external bore radiuses are going to be the topic of our talk today. For example, let's say that quantum dots have a bore radius of 46 nanometer. If their size is less than 46, basically, they are due to quantum confinement effect, their band gap is going to change with their size, and size can be synthetically very easily controlled, which leads to very easy processing. Yeah, they are soluble in most of the organic solvents. And due to that band gap tunability, now we can target those part of the solar spectrum which cannot be absorbed by today's materials. And the second important property is the multiple exton generation. That property targets this part of the solar spectrum, which corresponds to high energy photons. What happens during that process is we can create more than one electron hole pair due to absorption of a single photon. And then the absorption of photon above their band gap do not lead to thermalization losses, but the extra energy is used to create multiple extons. And the first example to that process has been shown in 2011. As you can see, the EQE, first time, the EQE higher than 100% is obtained for less large quantum dots with 0.722 electron volt band gap. And where we are now, we are at this point, as you can see, and as you can see, the slope is very steep, and in the last 10 years, it reached from 2% efficiency up to 16.6% efficiency. So therefore, they are considered as one of the most promising materials in this field. The first problematic issue related to quantum dot is their surface. As their size is very small, and most of the atoms are residing on their surface. Yeah? So therefore, surface atoms becomes very important. If we have a control over the surface, we have the control over everything. And if there are some defect sites on the surface, this leads to some defect states in the mid-gap, and we call those as mid-gap states, and this creates some trap states formation, and the electrons can be trapped on those by these mid-gap states. So our aim is to remove those mid-gap states and improve the photovoltaic performance. This is what we've shown for less large quantum dots, and we show that when some metal halides are applied to those quantum dots during the synthesis stage, we can heal those defect states on the surface, and those healing of those defect states leads to some crystal ordering, changes in crystal ordering, and also their stability can be controlled in addition to photovoltaic performance. As you can see, those passivated quantum dots are extremely stable under ambient conditions, whereas unpassivated quantum dots are prone to oxidation when we keep them in air. So this is one of the disadvantages of quantum dots. Yeah? Not less sulfide, but less ternite and lecterite are extremely air unstable. So therefore, controlling instability becomes very important. What happens when we keep them outside? Basically, they start to oxidize starting from their surface, and that oxidation advances into the core. So therefore, the size gets smaller and smaller due to that oxidation, and as the size gets smaller, we see a shift in their absorption. And this is one of the ways of controlling the kind of extent of instability or extent of oxidation. They've done a similar study for electrolyte quantum dots. Why electrolyte quantum dots are important? They're important because they have higher energy yield, but they are extremely air unstable. And what we've done, we've synthesized a series of electrolyte quantum dots with different sizes. And as you can see from their high resolution TEM images, their shape changes, yeah, as the size changes, starts from octahedral to cubo-octahedral. Yeah? And we discovered that the change of shape and change of size is also affecting the instability. The small size electrolyte quantum dots show a 20 nanometer shift in when they're exposed to air, but electrolyte quantum dots with large sizes, yeah, we see that they are extremely unstable. Yeah? They show a large shift, blue shift when they are exposed to air. We discovered that this is mainly due to the formation of these facets we called 111, and those facets we saw that those facets are extremely air unstable and they need to be passivated. And this is what we've done in this study. We applied some metal halides to the surface of quantum dots, and we healed those defect sites on the surface, and then they become very air stable when they're exposed to air. As you can see, even though for the larger quantum dots, we don't see any blue shift in air. And we also discovered that the instability can be due to many sources. And a simple catalyst, this is widely used catalyst, can become one of the main sources of instability. And as you can see, the uncatalyzed quantum dot is fairly stable when exposed to air, but the catalyzed quantum dot becomes extremely unstable. So then this shows that we must be very careful about synthetic conditions. Another parameter, synthetic parameter that plays significant roles in the stability of quantum dots is the stabilizing ligand concentration. So that OR, like acid, is used to stabilize those quantum dots in organic solvents. This ligand concentration of that ligand is very important. If it is used in excess, then the quantum dot is widely or is perfectly surrounded by those ligands, and they become very stable in air. But the same size quantum dot with less amount of those stabilizing ligand on the surface becomes extremely air unstable. So then this is another factor that controls the stability. So the question is how we are going to control that surface, how we are going to inhibit the mid-gap state formation. We need to get rid of those long insulating ligands and exchange them with shorter ones to improve the conductivity. If we're going to use them in photovoltaic cells, we need to exchange those ligands. But we discovered that ligand exchange is one of the main sources of air instability and main source of mid-gap state formation. As you can see, unpassivated quantum dots, when they are ligand exchanged with some organic molecules, easily oxidize in air, but passivated quantum dots are extremely air stable. Yeah? And also, we check their mid-gap state formation with absorbance spectroscopy, and we've seen that unpassivated quantum dots have some absorbance at the long energy side, which corresponds to the absorption of mid-gap states, whereas synthetic depassivated quantum dots doesn't have that kind of mid-gap state formation. Basically, this shows that the passivation method we use successfully remove those quantum dots. We can also see that effect from photoluminescence studies. Synthetic depassivated lead-charged quantum dots in solution have featureless photoluminescence and absorbance spectrum, as you can see. Whereas for unpassivated quantum dots, they have some folder in their photoluminescence spectra, which corresponds to mid-gap states. We also discovered that surface passivation modulates the cracking. We've used different types of passivating regions during thin film formation, and we discovered that if we use synthetic depassivated lead-charged quantum dots for the thin film formation, both the 1-1-1 diffraction pattern and 1-0-0 diffraction pattern is preserved, and the film has long range order, and the crystals are nicely organized. Whereas if we apply the same thing for unpassivated quantum dots, we've seen that for some of the regions, the 1-1-1 crystal, 1-1-1 diffraction pattern is lost, and then crystals are kind of we don't see a long range order, and they are not ordered in a way that we want for a photovoltaic cell, basically. Let's see how the photovoltaic performance is affected by the passivation. You're seeing the energy landscape, which is measured from UPS measurements. And as you can see, we've synthesized two quantum dots, which are unpassivated and synthetically passivated. They have band gaps which are a little bit different from each other, but this doesn't lead to a huge difference. And what happens when we apply another metal halide region during thin film formation, to an unpassivated laterite quantum dot. As you can see, when we use rubidium iodide region during thin film formation, both the valence band and the conduction bands are shifted downwards, and but when we use the same region for synthetically passivated quantum dots, the extent of that downshifting is not as severe as we've seen for unpassivated quantum dots. This shows that unpassivated quantum dots have lots of surface defects which are healed during that thin film formation, and this leads to a kind of huge downshifting of the energy levels, which is not severe for synthetically passivated quantum dots, which have already passivated surfaces. And when we fabricate some photovoltaic devices with them, we've seen that when rubidium iodide is applied to unpassivated quantum dots, the open circuit voltage decreases significantly, and this makes sense because the conduction band shifts to downward, and this we can explain this effect. And when we apply the same procedure for synthetically passivated laterite quantum dots, we've seen that open circuit voltage again decreases due to those shift in their energy levels, but the short circuit current increases 6 times. As you can see, the current was 2.1 milliampere per centimeter square, but for synthetically passivated quantum dot, it increased to 12%. And this leads to a doubling of the photoconversion efficiency. And the champion device that we got for synthetically passivated quantum dot had an open circuit voltage of 0.44, which is the highest in literature for laterite quantum dots. And this is this shows the importance of removal of mid-gap states, which also leads to the quantum dots which has the highest efficiency in literature for laterite quantum dots. And as you can see, the other very important effect from this synthetic passivation is their device stability. The synthetically passivated solar cells are extremely air stable, even when they are stored for 6 months. But the unpassivated quantum dots do not generate any photons. Photogeneration is a kind of stopped for unpassivated quantum dots. Thanks to you all. If you have any questions, I'm happy to answer.
Thank you, Demet Hocam. Such a nice recorded seminar. I believe there is no questions from the audience, so I believe I have to ask one question. Demet Hocam, if you compare the absorptivity coefficient or dielectric constant of your material with the silicon, so is it higher or lower, especially the absorptivity coefficient?
I'm not sure about silicon's dielectric constant and absorptivity.
Around 10 dielectric constants, such as, is it higher or lower?
These have a higher dielectric constant, if I'm not wrong. And but the problem is having a higher dielectric constant doesn't make any kind of advantage to our devices, because it just creates too many traps in our cells. But yeah, this is my answer. Thank you for your question.
Thank you, Demet Hocam. Maybe we can move to the now second speaker. Our second speaker from the NİDE Ömer Halis Demir University, Ali Altuntepe.
Yes, I am.
He's going to talk about hybrid transparent conductive electrode structure for solar cell application. Hello, Hocam.
I would like to say hello to everyone. Today, I'm going to talk about hybrid transparent conductive electrode structure for solar cell application. Firstly, let me check outline. I will talk about graphene, fabrication process of graphene, and characterization. Then we will talk about aluminum doped zinc oxide and aluminum doped zinc oxide graphene hybrid structure. We will discuss about fabrication process and characterization. Then I will examine AZU and hybrid solar cell structure, fabrication process, characterization. Finally, I will tell something about this issue generally. What is the graphene? Actually, we know this material. When we write something with pencil, we leave many graphene layers on the paper. Just I'm telling for your imagination. 1 millimeter graphite consists of 3 million graphene films. It means that we are talking about so thinnest material. On the other hand, graphene basic building block of other form of carbon, such as fullerene carbon nanotube. Graphene has most of attractive properties, such as 98% optical transmission, high mobility, high thermal conductivity. In addition, graphene is stronger than steel, conductive than silver, lighter than paper. These remarkable properties make it available for large-scale application area, especially solar cell. ITO, I mean indium tinoxide, is one of the available TCO, which is also commonly used. However, ITO has some disadvantage, such as limited resources, and ITO is brittle. For this reason, we investigating other type of TCOs. For example, doped zinc oxide, and in this presentation, I will be talk about AZU. In fact, I will provide some solar cell results with AZU and hybrid TCO, which consists of AZU graphene. There are a few methods for graphene synthesis. CVD provide large-scale and homogeneous graphene synthesis. The growth mechanism in CVD based on the decomposition of hydrocarbon gases at elevated temperature and the diffusion of carbon atoms onto a metal surface. Many parameters are important for graphene synthesis. Copper, nickel, or other metals can be used as substrate. Temperature growth time should be optimized for large-scale graphene synthesis. We used polycrystal copper as substrate. 30 minutes growth time was applied at 1000 Celsius degree for single-layer graphene synthesis. Graphene layer should be transferred for solar cell fabrication. For the transfer, we are using wet transfer technique, which is called polymer supported transfer. The polymer we used is PMMA. To begin, copper was coated with PMMA in spin coating. Then, copper is baked onto hot plate. After that, plasma cleaner was used in order to clean backside of copper. Copper was etched in the iron chloride solution. Graphene and PMMA are rinsed with diazide water. Finally, we can transfer graphene onto any substrate. Characterization is important to graphene, especially Raman characterization. Graphene has two main peaks, which are called G and 2D. G peak represents crystallinity of the graphene. 2D peaks can be called track peak of the graphene layers. In addition, graphene has another peak, D. D peak typifies the fact on the graphene structure. G and 2D peaks come with this peak. Zinc oxide properties can be enhanced by doping. Electrical and optical properties of zinc oxide can be improved by aluminum doping. Aluminum atomic radius is close to zinc. And also, aluminum atomic radius is 0.053 nanometer. zinc atomic radius 0.074 nanometer. So aluminum doping is easier for zinc. Aluminum getting zinc structure. There are a few methods in order to fabricate azio films, such as PVD, CVD, sol gel methods. Azio films were fabricated using sputtering magnetron technique in PVD. 10 different sets of samples with different thickness. We fabricated azio films from 50 nanometer to 500 nanometer. The reason we have investigated such a large scale is to find out the best film thickness in terms of optoelectronic properties. By the way, we didn't apply any pre or post annealing to fabricated azio films. When we check off the azio films, electrical and optical values, when we increase the azio film thickness, sheet resistance decrease. On the other hand, with increase of azio films thickness, optical transmission wasn't affected seriously. Generally, azio films optical transmission 80%. This result can be related with azio films crystallinity, because increase of the TCO's film thickness can improve crystallinity structure. So, sheet resistance of azio can be decreased with the increasing film thickness, and optical transmission weren't affected seriously. However, when we examine azio graphene hybrid structure, sheet resistance of that increase. This situation could be related with high sheet resistance of graphene. Considering of only sheet resistance is not enough to determine hybrid structure properties, because graphene has high mobility, high work function, so it can overcome handicaps onto hybrid structure. When we consider optical and electrical properties, 300 nanometer azio film thickness was determined optimum value. This figure shows 300 nanometer SEM image. In addition, we can see XRD pattern for 300 nanometer azio film. This film crystal size is about 48 nanometer. Also, we can check other values in the table. 1-inch azio and hybrid solar cell fabricated. Then cell efficiency was measured by solar cell simulator, so that azio and hybrid solar cell efficiency were compared each other. At this point, when we investigate azio and hybrid solar cell efficiency, azio solar cell has 14.5% efficiency, and hybrid solar cell has 15.5% efficiency. Solar cell efficiency was increased by graphene. Most of parameters are important for solar cell efficiency, such as fill factor and open circuit voltage. Fill factor was decreased in azio graphene hybrid structure. This situation related with graphene high sheet resistance, because high sheet resistance can be limited fill factor. However, there isn't a serious decreasing in the fill factor. On the other hand, when we check VOC values, VOC was increased with azio graphene hybrid structure, because graphene has more work function than azio has. Azio work function is 4 electrovolt and graphene work function is 4.6 electrovolt. So we increase of our solar cell efficiency. And generally, large-scale single-layer pristine graphene was synthesized. Azio films were fabricated using PVD. Hybrid TCE structure was fabricated by transferring graphene onto azio films. Silicon-based solar cell with azio and azio graphene as TCE were fabricated and measured in terms of efficiency. Thank you for your attention.
Thank you, Ali Hocam. Such
You're
a nice
welcome.
seminar. And I believe there is no questions from the
Yeah, hocam
audience.
aslında benim, so I have a question, if
Oh,
I
sure,
can.
Demet Hocam, buyurun.
Yes, I'm.
I just wanted to learn what leads to change in open circuit voltage.
Our open circuit
Does
voltage-
the energy levels changes when you dope zinc oxide with graphene?
Exactly at this point, generally we studied of the different type of the TCO and ITO, gallium doped zinc oxide, also aluminum doped zinc oxide. When we transfer of the graphene this structure, we increase of the VOC. Why? Actually, this is related with the work function of the graphene because we have higher work function. On the other hand, maybe at this point, fill factor is decreasing, and also when we check of the some literature studies about this issue, and they decrease of the fill factor at the same time because high sheet resistance of the graphene. And also at this point, when we apply of the doped graphene, because when we N-type doping or P-type doping applied of our graphene structure, we can decrease of the high sheet resistance. At the same time, we can balance of the fill factor at this point. On the other hand, we increase of with high sheet resistance because of the graphene work function. Also, when we compare of the other tissues, as I told you, such as ITO and also aluminum doped zinc oxide.
Thank you, Ali Hocam. There is one more question from the audience. Also, the fill factor is very low, of less than 1% to end up with more than 15% efficiency. Is true to have about 90% fill factor? If it is, what do you show in the presentation?
Actually, we fabricated of the 1-inch solar cell at this point. And also we fabricated of the solar cell manually. And at this point, we fabricated approximately 100 solar cell for the determining of our efficiency when we compare. Because when we cut off our solar cell with the manually, we can consist of some handicaps, also some problems of the solar cell structure. Also, I'm talking about just 1-inch solar cell. So we compared each other mostly, but now I don't have any result for these questions.
Ali, this is Raj Turan.
Yes,
your fill factor values are a little bit interesting or strange. So, I mean, is it 1% or is it 90%? What is that value? What is your fill factor value?
Just I will check.
I mean, you should check that, because if it is 1%, it doesn't mean anything. I mean, 1% cannot be 1%. 90%, it's too high. So this is not what we expect from such a structure. So maybe you can check that out if they are correctly determined.
Yes, Hocam, I will check this result.
Okay, good.
Any more questions? If not, let's move to the next speaker. Mona Bora is a PhD candidate in Micro and Nanotechnology Department at Middle East Technical University, where she received her master's degree. She has received her bachelor degree in electrical and electronic engineering from the University of Oromia, Iran. Her research interests include crystal silicon-based solar cell. And today she is going to talk about the selective chemical removal of subsurface laser modified silicon for photovoltaic. Mona?
Yes, thank you for a nice introduction, Hocam. My presentation is pre-recorded. Then I will join in question and ask for the session. Thank
Hello
you.
everyone, I'm Mona Bora from Metuguna. My topic of presentation is selective chemical removal of subsurface laser modified silicon for photovoltaics application. Silicon is important material in modern society, which has a variety of applications in the field of electronic and photovoltaics. The surface laser processing is well-established technology, which in many applications like edge isolation and surface microstructure fabrication and surface texturing or light trapping purposes. The left SCM image shows the micrometer size cone on a silicon surface, which is irradiated with femtosecond laser pulse at the wavelength of 800 nanometer. And the right SCM image shows using 1064 nanometer laser for laser texturing on multicrystal silicon. In many laser process, chemical treatment is required to remove laser-induced residues. So, the subsurface laser processing is beneficial because the current lithography methods don't allow fabrication of device or microelectronics directly inside the silicon wafer. Subsurface structuring enable us to create the 3D architecture, including microchannels, which did it before. In this process, similar to surface laser processing, further etching process is important and essential to reveal the subsurface structure for these applications. So there are different techniques to produce the thin crystal silicon slicing, includes chemical etching in highly concentrated potassium hydroxide and slim cut methods. But in these techniques, a large fraction of the crystal silicon thickness is wasted, and they are not able to reduce these techniques below the 100 micrometer. This is our work, which is already published. The curve-reduced slicing of bulk silicon is high commercial interested in photovoltaic industry. In this context, novel scheme alternative to wire cutters for silicon slicing is for achieving the slicing with minimal material loss. So we proposed the laser-induced silicon thin film slicing as a new technique in which the thin crystal slices with minimum loss of materials and controllable modification deep inside the silicon. In this technique, the nanosecond pulse fiber laser, which operates in 15 nanometer, is focused to the cross-sectional under the surface and is processed to create the structural modification at the subsurface. This video, this video is recorded from the infrared microscopy, and you can see the process zone, and the laser beam is focused moving inside the silicon. So, this work is focused on development chemical treatment which is applied to subsurface laser modified silicon. After the laser processing, the modified materials is exposed from 4 sides and etched away to unmodified region to produce the thin slicing silicon wafer. And our main challenges in this work is finding to suitable recipe applicable to different purpose with different sample size, and suitable etch rate for the laser modified region and unmodified part. And also the selectivity is important in which desired by specific application. And providing a less damage on the crystal silicon and better quality of surface morphology is important thing. In this experiment, we need to calculate the etch rate, selectivity, and fractal dimension analysis. So we use two samples, which is shown here, in per etch solution set. The laser processed sample includes this one, include the both laser modified and the unmodified region, and the other samples are unprocessed as a reference samples. So these samples are measured until 60 minutes with the interval of 10 minutes. So after this experiment, we obtained the etch rate, which is the mass difference of laser modified region over the etching time, and the selectivity of the ratio, which is a ratio of the etch rate of laser modified region over etch rate of unprocessed sample. And the crystalline silicon smoothness is represented by calculating the fractal dimension, which obtained from the SCM image after 16 minutes. So we adopted for this selective chemical etching, we adopted the MEMC etching, which is the solution which contains the copper nitride and nitric acid and hydrofluoric acid and acetic acid. We use the copper nitride based etching because it's very defect sensitive, which is effective not only on crystal silicon region, but also for laser modified region is suitable, and it's the chrome free and no hazardous waste and no toxic. In this component, we use the copper nitride as accelerating the reaction at the modified site, used as a catalyst, and the nitric acid as a main oxidizing agent, and hydrofluoric act as removing the oxidized part, and acetic acid for the smoothness of the surface morphology and diluting the solution. So, sorry. In order to achieve the smooth surface after laser processed silicon, we change the concentration of each these components with the aim to reach the high chemical process speed, I mean the etch rate, and also selectivity processed region only. Here is the effect of amount of copper nitride variation on the chemical process. The concentration of the hydrofluoric and nitric acid and acetic acid were kept fixed, and the amount of copper nitride changed from 0.75 gram to 2 gram. So you can see the etch rate graph and selectivity and the fractal dimension, I mean the surface morphology. As you can see, the etch rate of the laser modified region decreases as the amount of copper nitride increases up to 1.5 gram. However, the etch starts to increase with high amount of copper nitride, high amount of copper nitride in 2 gram. In addition, the selectivity shows a different trend in which in this set, the selectivity is highest for set 1. It belongs for 0.75 gram copper nitride. And that fractal dimension, as you see in the right side of the graph, shows a better surface morphology for this reference set. So we can say the effect of copper nitride is dominant on the selectivity. Here is the effect of hydrofluoric concentration on the chemical process. And here we change the concentration of hydrofluoric from 7.02 and up to 17.94. And as you can see, you see the high concentration of hydrofluoric in the solution damage the sample, which leads to poor fractal dimension, while it drastically increases the etch rate of laser modified part. And the effect of the higher hydrofluoric is more pronounced in laser modified region rather than unprocessed sample. However, the fractal dimension is steady for the low concentration. So here is also the effect of nitric acid variation. We also change the nitric acid concentration in these sets, and you can see the as you can see in these graphs, both the etch rate and the selectivity increases by increasing the nitric acid concentration. And it confirms that increasing the oxidizing agent increases the etch rate of the laser modified part more than unmodified part as a unprocessed sample. However, the fractal dimension is steady for low concentration, as you can see in this graph. And it's the increasement of the oxidizing agent leads to rough surface morphology as it expectable. So, as a summary, the selection of the component concentration depends on the desired application. Since the etch rate, selectivity, and surface morphology of subsurface laser modified region are well controlled during this experiment by varying the etching concentration of the components. And by decreasing the amount of copper nitride in the solution leads to fast and selective etching by having reduced the crystal silicon surface smoothness. And by decreasing the HNO3 nitric acid leads to low etch rate and selectivity while provides the smooth crystal silicon surface morphology. And some applications which may use small samples require high selectivity but low etch rate, which can be achieved by increasing the copper nitride in 2 grams in the etching solution. Thank you for your listening. If you have any question, I will be happy to answer them.
Thank you, Mona, for such a nice study and recorded talk. There is no question from the audience right now. Any question? Rashid Hocam, any questions to Mona?
I have already asked many questions to her, but maybe what do you think about the large area applications? I mean, in your cases, your samples are having small area. Do you think this is applicable to large area production solar cells?
Yes, Hocam, we are actually working on that for this. It's important in industrial application. But in this work, we are working on the improvement of the chemical etching. But for the next step, we want to be the large area as large as possible. And it's for the next plan.
Okay. Good, thank you.
Thank you.
Thank you, Hocam. Thank you, Mona.
Thank you.
So we can move to the next speaker. Thank you, Mona. Next speaker from the, again, Metür Günam, Parisa Sharif. She got her BS degree, Electric and Electronic Engineering from the Tabriz University, Iran, MS degree from the Metür Electrical and Electronic Engineering Department. Currently, she's a PhD candidate in micro nanotechnology. Today, she's going to talk about the flexible polymer solar cell with modified multi-layer graphene electrode.
Ali Hocam, thank you for your nice introduction. Hello, welcome to my presentation. Today I will talk about flexible polymer solar cell with modified multi-layer graphene electrodes. Well, polymer solar cells perform exactly the same function as any other types of solar cell, the conversion of photons into an electrical current. Polymer solar cells uses conductive organic polymers for light absorption and charge transfer. Compared to silicon-based devices, polymer solar cells are lightweight, inexpensive to fabricate, they are flexible, easy to integrate, and polymer solar cells have the potential to exhibit transparency, suggesting application in windows, walls, and flexible electrodes. In this work, we use graphene as an anode in polymer solar cells. So what is graphene? The first two-dimensional material ever discovered. It is one-atom thick and carbon atoms arranged in a hexagonal lattice. It is the strongest, lightest, and most conductive material known to man. Graphene matches indium tin oxide performance in its basic state. If we want to compare the graphene with indium tin oxide is more costly. It is very expensive material, but the production process of graphene has been improving and becoming cheaper. Indium tin oxide is a rigid and fragile material, but graphene is flexible and mechanically strong, so it can be incorporated with flexible solar cell. Transparency of indium tin oxide is around 85%, but graphene shows more transparency than indium tin oxide. Indium tin oxide has a mobility of up to 70, but graphene has mobility up to 20,000. Well, one kind of polymer solar cells is heterojunction solar cells, which can be bilayer heterojunction or bulk heterojunction. In bilayer heterojunction, the donor and acceptor are separated materials, but in bulk heterojunction, the donor and acceptor are in the same solution. And in this picture shows the working principle of polymer solar cell. Light absorbs with donor and exciton formation happened there. Then the excitation diffused to donor acceptor interface. Charge separation happened there, and at the end collection of charges happened at the corresponding electrodes. CVD grown graphene, we use CVD method for growth the graphene. CVD is a way of depositing gaseous reactant onto a substrate. The way CVD works is by combining gas molecules, hydrogen, methane, and argon in a reaction chamber. A catalyzed substrate is used for decomposition of carbon atoms from a gas, for example, methane, flowing through the CVD chamber. With the efficient controls of the gases flowing through the CVD chamber, large area single crystal graphene has already been reported. As a catalyzed substrate, we can use platinum, copper, and nickel. We use copper here as a catalyzed substrate. Come to growth of graphene. As I said, I use copper, but called rolling copper in graphene growth as a substrate. Because of the deformation in the grain structure of this kind of copper, it is very suitable substrate to growth uniform and single layer graphene. It is my process flow. After acid pretreatment of coppers, I put them in CVD chamber. After argon cleaning and hydrogen annealing, growth will be done by exposing of methane gas. And this is my Raman spectrum of my graphene. Sharp to the peak proves the single layer nature of graphene. So, in compare of indium tin oxide, graphene has high sheet resistance. To solve this problem, chemical doping is done. Graphene is a zero band gap material, and by doping it with nitric acid, a shift can be happen in Fermi level of graphene. So in this way, we can have a p-type graphene. I tried two different methods for doping of the graphene. One of them is interlaying chemical doping and the other is last layer doping. After transferring the graphene to the PET substrate with lamination technique, I soak my anode to nitric acid, and between these two methods, last layer doping was successful, and I can decrease the sheet resistance to 29 ohm per square. This is a paper which published recently by Churpan Research Group, and it is about polymer solar cells which try new polymers on indium tin oxide anodes. And they got the maximum PCE from PO polymer. We tried the same polymer on graphene PET anodes. I mean, we use the same polymer with the same weight-to-weight ratio, acceptor and donor, and by adding 1% additive. It is my device structure. We have a PET substrate as a transparent and flexible substrate, transferred multilayer graphene, doped multilayer graphene as an anode. We have PSS IPA as a fault transport layer, PCBM and PO as an active layer, and at the end, lithium fluoride and aluminum as a metal, and P-type conjugated polymers and N-type molecules consist of our active layer. Well, these are our results. IV and EQE characteristic. In this table, we compare the results from polymer solar cells with different anodes, PET and graphene, and glass and indium tin oxide. As you see, in case of VOC, they are same and close, and their power conversion efficiency is also close, while our fill factor is lower than indium tin oxide ones, but because of high current density, we get a good power conversion efficiency. I believe with more optimization, we will increase fill factor and get a polymer solar cells with higher power conversion efficiency. And we get a EQE more than 80%. So as a conclusion, graphene as a flexible and transparent electrode can be used instead of indium tin oxide in polymer solar cells. Because of high sheet resistance of graphene in compare of indium tin oxide, the VOC and current density of polymer solar cells are limited. But by engineering of sheet resistance and work function of graphene, these values can be modified. Polymer solar cells with graphene anode have been fabricated with 7.46% power conversion efficiency. As a future works, some optimization experiments will be done to improve fill factor of polymer solar cells. We will try different kind of additives with different ratios and with different thermal and solvent annealing to polymer to have a uniform solution, and in order we will increase the fill factor, and at the end we will get a higher power conversion efficiency graphene solar cells. Thank you for your attention.
Thank you, Parisa, for such a nice work and the recorded talk, of course.
You're welcome.
There is no question from the audience right now. Any question?
I have a question, Ali Hocam.
Go ahead, please.
You get 16 milliampere per square for modified anode, but 14 for ITO. I just wonder from what part of the spectrum you gain that photocurrent, in the UV region, in the visible or infrared?
Excuse me, I cannot understand your question.
So you showed us an EQE spectrum.
Yeah.
And you told that you get more current from modified anodes you prepared for your study, right? I just wonder from what part of the spectrum you gain from this structure. In the UV part, visible or infrared?
Between 300 till 1000 wave number.
Oh, okay, so you say that for a wide wavelength region, you gain photocurrent. Is it correct?
Yes, it is.
What about the transparency? Is it much more transparent for the ITOs you prepared?
Actually, one layer of graphene absorb 3% of the light. Here, our anode is around 7 layer of graphene, but till date we not measure the absorption, but we think it will be around 80% in best case.
Oh, okay. So for ITO, the transparency is around 85. So I expect your EQ to be lower in the UV region. If you
yes.
do that.
Yes, but because we modified the graphene and transferred to the PET, because of the thin thickness of the PET, we can spin coat the thicker active layer, and because of that I think we have a better VOC and current density, but it is soon to talk about that, because we still not have TEM images of our active layer, but we have appointment from Merlab. After TEM images we can talk about precisely, I think.
Okay, that makes sense. If you have thicker devices, gaining more current
yes.
is just answers my question. Thank you, Parisa.
Welcome.
Thank you, Demet Hocam. There is one more question from the audience, Parisa.
Okay.
Fill factor is due to the which terminal resistive losses? Lithium fluoride aluminum or the other side?
Again, I think we will optimize our device with I think more value of additive, and I think with different value of annealing, I think we can increase the fill factor. This work is continue. We catch this power efficiency in our second measure, our second experiment, I think with more optimization in our process, we will increase the fill factor, I believe.
No. The question is asking where the terminal resistive losses from the lithium aluminum side or from the ITO side?
I think we don't have ITO side. We have graphene.
I mean graphene. Yeah, graphene.
I think because of graphene side. Because we have the same device with ITO and lithium fluoride, and there is, I compare in my presentation, the fill factor with that device, lithium fluoride and indium tin oxide, has a good performance in case of fill factor. The loss in fill factor is because of graphene.
Okay, there's one more question. Did you measure the work function of the graphene anode layer, or?
Yes, yes, it is around 4.6 electron volt, but we are not put it in our presentation because after modifying my graphene and doping, I didn't measure the work function, so I didn't put that data in my presentation.
Both, one more question.
Okay.
But both has low fill factor.
Both of them?
Has low, yeah, Nisam is asking. Both have low fill factor.
Let me
Both
check.
means what, Nisam?
I cannot understand the question. Hocam.
Just I am waiting, might be Nisam will write down the question again. Both has low fill factor. Both means electrodes, Nisam? Okay, let's move to the next talk. Thank you, Parisa.
Welcome.
Our next talk is Nuray Çelebi Hocam from the Ankara Yıldırım Beyazıt University. Today she is going to talk about star-shaped zinc oxide, cerium oxide, Z-shim heterostructure for photoelectrochemical water splitting. Hocam. Nuray Hocam is here.
Hello everyone, my name is Furkan Soysal. I am an assistant professor at Ankara Yıldırım Beyazıt University. I will present you our recent study titled Star-Shaped Zinc Oxide, Cerium Oxide, Z-Scheme Heterostructures for Photoelectrochemical Water Splitting. The content of the presentation is hydrogen, photocatalytic hydrogen production, photocatalytic systems. Aim of this study is synthesis of heteronanostructures, characterization, electrochemical characterization and band properties, photoelectrochemical measurements, and conclusion. Hydrogen is a renewable energy source and a zero-emission fuel, which is more efficient than petroleum products. And although there are many hydrogen production methods, direct water splitting have attracted great attention in recent years. So, what is photocatalytic hydrogen production? By water splitting, we use a semiconductor which plays significant roles in major processes. The first one is bandgap photoexcitation to induce formation of electron-hole pairs, migration of delocalized charge carriers to the surface of the photocatalysts, and provide active sites for the subsequent redox processes. So we can classify photocatalytic systems in three main groups. The first one is single component photocatalysts, which is only comprised of a single component. And we can have type 2 heterojunction and Z-scheme photocatalyst systems. In single component photocatalysis, we have only one particle, and this particle must have sufficiently small band gap to be activated by light, and also a considerable large over potential to enable redox reactions. But these two concepts are conflicting. If the photocatalyst have small band gap, it also has a small over potential. And these particles suffer from rapid recombination of photogenerated electron-hole pairs. So type 2 heterojunction is mostly used for water splitting to improve charge separation efficiency and enhance the photocatalytic performance. So the gas evolution occurs in two separated photosystems, but the redoxability of the photocatalytic system is weakened due to the migration of electrons and holes to the more electropositive conduction band and electronegative valence band. And in recent years, Z-scheme photocatalyst systems have gained much attraction. This is a configuration of two photocatalysts and an electron mediator in between to perform water splitting through two-step photoexcitation process. And we can have a small band gap and suitable band edge position with considerable large over potential in the system. And we can also suppress electron-hole pairs recombination. And water splitting occurs in two isolated photocatalysts, in which one of them serves as the reduction site, while the other as an oxidation site. And electron mediator is used to facilitate the electron flow between the two photosystems. So upon photoexcitation, electrons from the valence band of the both photosystems will be excited to the conduction bands, leaving holes in the valence bands. Then the photogenerated electrons in the photosystem 2 will subsequently transported to the electron mediator to recombine with the holes from valence band of the photosystem 1 via ohmic contact. So the aim of this study is to construct a suitable heterojunction between two semiconductors with appropriate band gap for enhancing charge separation, thus increasing photoconversion efficiency for hydrogen evolution. We used zinc oxide because it's low cost, non-toxic, and has high physical and chemical stability, but suffers from a wide band gap and also recombination of charge carriers. So we used cerium oxide because it has abundant oxygen vacancies, a strong redox ability, a stable molecule, and low cost. Also has a suitable band gap position when combined with zinc oxide. And as an electron mediator, we used polydopamine. Also, we synthesized zinc oxide in star shapes, so we increased the number of active sites. The synthesis of heteronanostructures were performed in 3 steps. First, star-shaped zinc oxide. Then zinc oxide nanoparticles were covered with polydopamine. And finally, cerium oxide nanoparticles were formed on zinc oxide polydopamine nanocomposite. First, to synthesize star-shaped zinc oxide, we prepared the DMF water mixture, and used zinc acetylacetonide and PVP, and this mixture was we set pH to 10 with sodium hydroxide solution, and we used an autoclave for a hydrothermal reaction at 140 degrees Celsius for 90 minutes, and using centrifugation decantation method, we washed several times with acetone and ethanol mixture. So the obtained zinc oxide particles were added to tris hydrochloric acid and sonicated for 10 minutes. Then dopamine hydrochloride was added under vigorous stirring at room temperature for 3 hours. And the obtained product was washed several times with water. For cerium oxide nanoparticles, we used cerium nitrate hexahydrate aqueous solution, added zinc oxide polydopamine nanoparticles, and stirred for 2 hours at room temperature. After the addition of sodium hydroxide, we stirred another hour at room temperature, and obtained product was washed several times with water, and we obtained zinc oxide polydopamine cerium oxide nanoparticles. And you can see the scanning electron microscopy images of star-shaped zinc oxide nanoparticles. As you can see, the morphology is obtained by this synthesis method, and the particle size of the product is approximately 400 nanometers. And the image of star-shaped zinc oxide coated with polydopamine. And in this image, you can see the cerium oxide nanoparticles on zinc oxide polydopamine structure. The XRD results of zinc oxide nanoparticles can be seen here, and the diffraction patterns reveal that the structure is word-side hexagonal phase. And the XRD results of zinc oxide polydopamine cerium oxide, and we can see the cubic phase of cerium oxide. And the XPS results of zinc oxide polydopamine, and zinc oxide polydopamine cerium oxide. We see the zinc 2p1/2 and 2p3/2 bands here. But in zinc oxide polydopamine, we have a shift to higher energy levels and this reveals the coating of polydopamine successfully. Also, there is another shift to the higher levels when a cerium oxide is introduced. So we have successfully synthesized the photocatalyst. And cerium 3D spin orbital electrons reveal that the cerium oxide nanoparticles are comprised of cerium 4+ and cerium 3+ with a majority of cerium 4+ ions. Electrochemical measurements were performed by Gamry reference 3000 potentiostat galvanostate. We used 0.1 molar sodium sulfate as an electrolyte. The working electrode was a photocatalyst modified FTO glass. As a reference electrode, we used silver chloride and platinum as a counter electrode. And the light source was visible LED light with a power density of 30 milliwatts per square centimeters. So the electrochemical characterization and band properties. We have Modt-Schottky plots of cerium oxide, zinc oxide synthesized separately, and the flat band potential of cerium oxide is minus 0.1 volts, and the flat band potential of zinc oxide is 0.3 volts. And for the nanocomposites, zinc oxide, polydopamine, cerium oxide, we can see the flat band potentials of both photosystems here. So also from tau plots, we revealed the band properties of zinc oxide and cerium oxide, and we calculated the band gap separately because zinc oxide is a direct band gap particle and cerium oxide has an indirect band gap. The band gap of zinc oxide is found to be 3 electron volts and cerium oxide 3.1 electron volts. And we used the Mulliken electronegativity equation to calculate conduction and valence band energies of the particles. The conduction band energy for zinc oxide is minus 0.2 electron volts and valence band is 2.8 electron volts. The conduction band energy of cerium oxide is minus 0.49 electron volts and valence band energy is 2.61 electron volts. And the photoelectrochemical measurements of our photocatalyst. And this one is linear sweep voltammetry. As you can see, bare zinc oxide nanoparticles shows no response. But our photocatalyst under dark shows a current density of approximately 25 microamperes per square centimeters. But when illuminated, the current density reaches up to 250 microamperes per square centimeters. And we have TEFL plots here for bare zinc oxide and our photocatalyst under dark and light conditions. The slope for bare zinc oxide is 117 millivolts. Our photocatalyst under dark and light is 90 millivolts and 38 millivolts under dark and light respectively. So the photocatalyst shows a decrease in the slope under dark, and when illuminated we see a dramatic decrease in the slope. The incident photon to current conversion efficiency, here we have the bare zinc oxide showed no response. Our photocatalyst under dark showed a 1% efficiency, and when illuminated, efficiency reached up to 9%. And applied bias to photon efficiency, also a similar behavior for bare zinc oxide and our photocatalyst under dark, and we reached 0.8% efficiency under illumination. So in conclusion, we have successfully synthesized the star-shaped zinc oxide and cerium oxide Z-scheme photocatalyst with polydopamine as electron transfer mediator for photoelectrochemical hydrogen generation. The presence of polydopamine resulted in the efficient accumulation of electrons and holes in the conduction band of cerium oxide and valence band of zinc oxide, respectively. The main advantages for polydopamine as an electron transfer mediator was the enhancement in light absorption ability of the catalyst, and it enabled faster interfacial charge transfer and more efficient separation and transfer of photo-generated electron-hole pairs. And the performance of the photocatalyst is excellent thanks to the rapid separation and transfer of photo-generated electrons from the conduction band of zinc oxide onto the valence band of cerium oxide. These are our references, and thank you for listening to me.
Thank you, Hocam, for such a nice work. I will ask one question, Hocam. When you compare the performance of your photocatalyst with the literature, what can you tell us about it?
Ali Hocam herhalde
hocam
yok yani teknik problemden dolayı belki de şey oldu. Gittiler yani.
Evet.
Şu anda bağlı kimse yok. Bir sonraki bence geçebiliriz yani.
Evet, geçelim de bitirelim bari. Okay, next speaker from the Romania, Professor Laurentiu Fara from the Polytechnic University of Bucharest. He's going to talk about optimized copper oxide crystal silicon 10 meter junction solar cell experimental and modeling investigation for defect analysis. Professor Fara.
Laurentiu, are you with us?
Yes. Yes.
Yeah, okay, good to hear.
Presentation.
You are with us. How are you?
Yes, the presentation was sent already.
Yeah, okay.
My presentation entitled Optimized Copper Oxide Silicon Tandem Heterojunction Solar Cells Experimental and Modeling Investigation for Defect Analysis is based on international projects, respectively ERANET program. The project is called SORHET, this is the acronym. Within this project cooperated two units from Romania, Polytechnic University of Bucharest, and Research Institute for Optoelectronics, INOE, and two units from research units from Norway, respectively Institute for Energy Technology and University of Oslo. The outline of my presentation contain an introduction, the presentation of solar cell concept, experimental approach. It contains the technology for thin film deposition by sputtering system, characterization of films, morphological and optical characterization, some aspects regarding physical parameters of copper oxide in films, current voltage characteristics for metal oxide. The next point is regarding the modeling of solar device and simulation results. Another point is regarding the analysis of the interface defect by model investigation. This is very important point, the analysis of the defect. And there are considered the modeling of zinc oxide, copper oxide top cell, effect of the interface defect on cell performance and the behavior of conduction band energy. And the last point of the presentation is regarding the conclusions. Here is presented the abstract of the article. Regarding the introduction, we have to consider that the cost reduction of the technology based on crystalline silicon solar cells allows to promote silicon-based tandem solar cells with based on metal oxide materials. This is important because will allow to have lower cost. Copper oxide is an attractive material for PV applications. This is a P-type semiconductor with high optical absorption and a band gap of about 2.1 electron volts. Copper oxides have to be combined with N-type oxide material like zinc oxide. In this case, we could obtain a heterojunction subcell. This is based on low-cost metal oxide. And the top subcell is combined with the bottom subcell based on silicon. We obtain, in this case, an efficiency of 14% for the top subcell, but the theoretical efficiency is higher, about 20%. And there is possible to consider further investigation in order to increase the efficiency. And an important point is regarding the tandem concept of solar cell. Copper oxide is photoabsorber, and as we considered that this material has high absorption coefficient, sharp absorption edge, high carrier mobility, and the highest conversion efficiency experimentally obtained is about 8%. The tandem solar cell is constituted from two subcells. The diagram of the tandem heterojunction is represented in the figure 1. There are two subcells, the top subcell based on heterojunction zinc oxide, copper oxide, and the bottom one based on silicon. The low energy photons are transmitted through the top subcell, while the high energy photons are transmitted to the bottom subcell. In this case, we could obtain theoretically from point of view, theoretical point of view, an efficiency possible higher than 30%. Regarding the experimental approach, it is very important to have some words about the experimental approach. The deposition of thin films, copper oxide and zinc oxide, is allowed by a sputtering system. This is the magnetron sputtering system. Here in the figure 3 is presented the heterojunction solar cell based on the sputtering deposition of metal oxide. Regarding the morphological and optical characterization of the top subcell, we have to consider that the morphology of copper oxides in film samples was investigated by scanning electron microscope and also by atomic force microscope. And we have considered also for X-ray fluorescence measurements and X-ray fluorescence analyzer. The thin film thickness and complex refractive index were determined by spectroscopic ellipsometry. At the same time, we have to consider that the optical band gap of the copper oxide film was determined from ultraviolet spectrophotometer measurements and room temperature Hall effect measurements were carried out for using the underpow configuration. These measurements will be useful for the characterization of physical parameters of copper oxide. The main physical parameters are the Hall mobility, film resistivity, and the Hall concentration for 500 nanometer thick, as there are two cases, as ground and annealed copper oxide deposited on quartz. And these parameters could be obtained based on Hall effect measurements. The results are presented in this table, table number 1. Also, another important point is regarding the current voltage characteristics for metal oxide heterojunction and then solar cell. It is remarked the rectifying behavior, but there are two problems to be solved in the next future based on further research: stability and reproducibility. Another point important in our presentation and in our contribution is regarding the solar device modeling. And here are presented some simulation results. Numerical modeling was based on 2 simulation software, Silvaco Atlas for the zinc oxide, copper oxide heterojunction top subcell, and PC1D, OCA2 for the bottom silicon subcell. And the main aspects regarding this software are presented in the figure number 5 and number 6. Buffer layer materials and performance of the top subcells could be studied based on the Pvcon modeling, and an optimizing top subcell structure for the buffer layer could be considered. The influence of the material characteristics of the buffer layer on the energy performance of the top subcell was analyzed. And the main results are presented in the table number 2. We have to stress that the most important material is zinc oxide. Here are the main characteristics for the zinc oxide. Current, voltage, filling factor, and efficiency. Regarding the modeling of the silicon bottom subcell, the software we used was OCA2 platform, and we have considered the comparison with the experimental data. We have the quantum efficiency, external quantum efficiency for the silicon bottom subcell, and the current voltage characteristics. And it is remarked that for the both cases, the experimental curve and modeling results are very close. An important point in our contribution is the analysis of the interface defect by modeling investigation. It is important to understand that the study of the interface defect is essential for a realistic approach to the modeling of tandem heterojunction solar cells. It was considered the modeling of zinc oxide, copper oxide top subcell, the effect of interface effects on cell performance was studied, and we consider the analysis of feasibility of heterojunction and metal oxides, the influence of defects from the IDL defect layer. The dependence of the electrical parameter of the solar device to the defect of IDL for different thicknesses are presented in the next figure. Figure number 9, A, B, C, and D. And here we have the presentation of the current open circuit voltage, filling factor, and efficiency for different thickness and function of IDL defect density. It is remarked a significant reduction in the energy performance of the tandem observed for defect density in IDL over 10 to 19 centimeter minus 3. And for this reason, the thickness of IDL was fixed at 5 nanometers. And also the defect density was fixed at 10 to 18 centimeters to minus 3. And another interest in the defect analysis is regarding the behavior of conduction band energy. The behavior of the conduction band for different defect densities of IDL with the fixed thicknesses of 5 nanometers was analyzed, and an increase in the band gap between the buffer layer and the IDL for a defect density above 10 to 19 centimeters to minus 3 could be remarked, and that is important that for decreasing of the performance of solar cells. The behavior of the conduction band for different copper oxide layer acceptor concentration was studied too, and it is remarked a significant increase in the band gap for a concentration above 10 to 16 centimeters to minus 3. And that results performance decrease is obtained. Okay, the last point of my presentation is regarding the conclusions of the contribution. As I already told, our contribution was based on the cooperation between the research team from Norway, from IFE and the University of Oslo, as well as from Polytechnic University of Bucharest, my university, and Institute of Optoelectronics from Magurele, close from Bucharest. The main conclusions could be considered as follows: an improved structure of tandem solar cells based on a combined zinc oxide, copper oxide heterojunction subcell with silicon solar subcell is obtained. Four-terminal tandem configuration of metal oxide solar cells is essential for the best results regarding the performance of the solar device. The models, simulation models, are very useful for design and optimization of the tandem solar cells. And for that, there are important to be used material parameters from experimental characterization. Another interesting conclusion is regarding the experimental implementation of metal oxide heterojunction solar cells. And we have highlight the current voltage characteristic in this case. The theoretical conversion efficiency above 30% could be obtained from theoretical point of view. And the last point is very important for the experimental investigation. It's based on numerical modeling defect analysis, and we could obtain that the defect, interface defect, and band offset of the copper oxide heterojunction solar cell reduce top cell performance. It is very important. Here are the acknowledgements. Selected references, especially based on my own research results, published in different international journals or presented in different international conferences. Thank you for your attention.
Thank you, Professor Laurenti, for your nice work. Any question from the audience?
Maybe I can ask a question.
Raşit Hocam, please go
Yeah,
ahead.
it's me. Yeah. So, yeah, okay. Hi, Laurenti. How are you?
Yes, thank you. Thank you.
I just want to ask you.
I'm very happy to see you again.
Sorry?
I'm very happy to see you again.
Yeah, I am happy to see you again.
I remember it was 4 years ago.
Yeah, it's a cost conference. I think we were together a long time ago. How are you? How is it going in Romania? Everything is fine?
Yes, it's okay.
Okay, good. My question, have you ever tried to use this fabricate experimentally, this tandem solar cell?
This is a problem. It's a big problem. It's possible to, but until now we have not obtained the experimental results are not very convincing for a possible development of this technology. One of the reasons could be the stability of this. Stability is one of the problems. And also, as I presented in this work, the defects, the interface defects are also a possible, and the experimental results, okay, are in general experimental results were developed, especially at Norway, at Institute of Physical Technology in Keller, Norway, but they didn't obtain the satisfactory results, and that is all this work was based on ERANET project developed in 4 years between 16 and 19, 4 years. We know that there are also other research groups in the world that are also working on metal oxides, silicon based, but in Japan, I remember it is a very strong group, but I don't know that they succeeded to develop experimental
results
approach convincing for the industry. That is the problem. It's not not yet convincing. Maybe perovskite could be a solution. Maybe is very similar with this. Perovskite solar cells could be very similar, but metal oxide is very interesting, and but there are some problems to be solved. Okay.
Okay. Thank you, Laurent. It was very nice to see you. Ali.
Thank you, Rafi. Thank you.
Thank you, Professor Farah, for sharing your recent work with us. I believe this is the end of this session. So thank you all for your participating. Hope to see you tomorrow. So
thank you, and I apologize for the technical problems we have had today. But this is the first time we are doing such a conference, so maybe it is not very. I mean, it might be normal to have some technical problems. So maybe I hope next day we will not have any such problem next 2 days. So okay, thank you for your attendance.
Thank you.